webinar of today, Storage Technology in Multi-Energy Careers and Industrial Environment in the SINNOGENES project. This is Matteo Troncha, and I'm representing ISGAN, which hosts this webinar. ISGAN is the short name for the International Smart Grid Action Network, a technology collaboration program of the International Energy Agency. ISGAN is also an initiative of the Clean Energy Ministerial, formally established in 2011. ISGAN creates a strategic platform to support high-level government attention and action for the accelerated development and deployment of smarter and cleaner electricity grids around the world. ISGAN consists of 28 contracted parties. Their nominated representatives form the executive committee, headed by the Presidium and assisted by 2 co-secretariats. The work of ISGAN is organized in several working groups that deals the entire value chain of smart grids. ISGAN's vision is to accelerate the progress on key aspects of smart grid policy, technology, and investment through voluntary participation by government in projects and programs. ISGAN activities focus on 5 principal areas: policy standards and regulation, finance and business models, technology system development, workforce skills and knowledge, users and consumer engagement. ISGAN facilitates the dynamic knowledge sharing, technical assistance, peer review, and project coordination among its contracted parties. The value proposition of ISGAN relies on conferences and workshops, policy and technology briefs, discussions and technical papers, casebooks, and webinars, like this one. Within ISGAN, virtual learning offers the ISGAN community means of rational and continuous technical skills update in the field of smart grids. The virtual learning is proposed as a set of e-learning and reading core modules dealing with the entire value chain of smart grid. The webinar today concerns the storage technologies in multi-energy careers and industrial environments and the development of the SINNOGENES project. The EU-funded SINNOGENES project addresses the European Green Deal and the long-term strategy for decarbonization, emphasizing on electrification and renewable energy deployment. It focuses on innovative energy storage solutions to tackle massive penetration of renewables, the electrification, and the residual low variability. The project integrates storage beyond current capabilities, promoting sustainability and scalability. In this presentation, we tackle the SINNOGENES storage innovation targeting the coordination of multi-energy careers and the industrial environment. The speakers of today are Ilias Zafeiropoulos from UBTech Energy, Rashid Amishbai Kansal from DLR, Ricardo Silva from Inestec, and Angel Hernandez Jimenez from CMAT. Feel free to use anytime the question and answer tool to pose your questions. The speakers will be happy to answer to your questions at the end of the presentation. The webinar recording will be available as usual through the ISGAN YouTube channel. Okay, now it's time to leave the floor to Ilias to start with the technical part of the webinar. So I kindly invite Ilias to start sharing the screen.
Thank you, Matteo. SINNOGENES is a project that deals with storage innovations for green energy systems. It tackles with a critical need for innovative storage solutions for environmental sustainability and increased penetration of the clean energy. As we see that the effective storage plays a pivotal role for the power system reliability, resilience, adequacy, and quality of supply. And it targets to identify the technical requirements for multi-vector storage services as per European and national regulatory frameworks. It also will develop and test technologies for the connection and uses of energy storage systems in existing platforms, ensuring multi-vector interoperability across consumers, markets, devices, and energy carriers. The objectives of the project is to develop and showcase a versatile suite of energy storage technologies, thermal, electrochemical, electrical, and mechanical storage systems, to create optimization tool for the collective potential of storage for energy arbitrage, peak saving, and flexibility services, to harmonize the energy storage solutions with the local renewable sources, to integrate innovative storage solutions into real-world scenarios, demonstrating their practical impact and effectiveness, and to engage diverse end users and sectors to provide practical, scalable, and economically viable energy storage solutions. So, SINNOGENES covers a plethora of sectors and applications involving widely adopted and commercialized options like hydropump storage and lithium-ion batteries. Emerging technologies still in R&D and implementation phase, such as power-to-gas, which is considered a potential source of low-cost, long-duration energy storage. Technologies with significant diversity in terms of their operational features and technological maturity, factors that will significantly influence their respective roles within the power grid. This is a graph of the various technologies that the SINNOGENES project is demonstrating in field applications, starting from ultracapacitors flywheel, going to lithium-ion batteries, flow-based batteries, thermal heat storage, hydropump storage, and power-to-gas storage, with different time frames and different level of distributed or bulk services. This is an outline of the demonstrations that we have in our projects, which our project consists of 27 partners, 6 demo sites in 5 different European countries, involving different environments and demand sectors, and also involving cross-energy carrier integration potential via coupling electricity with heat and hydrogen storage. The first demonstration is in Portugal, engaging batteries, thermal storage, and electrolyzers in a large industrial microgrid. The second demonstration is in Soria, Spain, involving geothermal energy potential for district heating in urban microgrid. The third demonstration is also in Spain, Huesca, involving a local energy community. Demonstration 4 is in Germany, where optimal integration of heat and electricity storage is demonstrated in a small industrial microgrid. Demonstration 5 is in Greece, Ikaria, engaging a hydropump storage in a digital twin in a non-interconnected island. And the demonstration 6 is in Switzerland, Geneva, where we have energy storage and distribution of hydrogen to urban and freight mobility. So the activities include a batch of integrated energy management tools and digital services for energy storage technologies with different time horizons, short-term, medium-term, long-term horizons, and several flexibility services, frequency regulation, black start, voltage support, congestion relief, and demand response. The applications on field and simulation studies, planning and operation of energy storage systems locally, management of hybrid energy storage technologies to provide flexibility services to energy system operators, increasing operational efficiency via energy sector coupling, planning of interconnections between remote areas, leveraging energy storage for energy efficiency and grid flexibility in the transport sector, and of course, the resilient operation of industrial microgrids and energy community, leveraging renewable energy resources, thermal energy, and hydrogen storage. Apart from that, we have environmental and business value, life cycle analysis, and life cost analysis provided to assess the life cycle, environmental and economic impact of the SINNOGENES technologies, considering predefined key KPIs, key performance indicators. We have also the development of business models for energy storage technologies to achieve the market uptake across Europe, leveraging the output, of course, from the environmental and economic impact assessment. And also we have a detailed techno-economic analysis evaluation of the project demonstration activities using the Artelis Crystal Supergrid modeling platform. This is the plan of the various activities in the project. We have completed the pre-development phase, including the analysis of technical and market compliance requirements, the definition of the business use cases, the design of the main SINNOGENES ICT architecture, and we are currently in the development and realization phase, where the SINNOGENES individual tools are developed, the ICT architecture, and we prepare the field deployments and the integration of the innovations. Then we will have the demonstration campaigns and, of course, the valorization and scalability, replicability analysis of the technologies. This is all from my side.
Yeah, thank you, Ilias. Now I'll take over. Hello from my side, everyone. I'm Rushit Kansara, representing German Aerospace Center as a part of the SINNOGENES project. I'll share my screen now. I hope it's visible. So I'll be presenting today what we have done like as DLR as a part of SINNOGENES so far and what what are our next future steps and what is the conclusion so far. Yeah. So as already explained, there are so many fossil-based production plants which still exist in Germany or all over Europe. And what we are trying to do with the SINNOGENES project, or at least TLR, that we are trying to implement a new novel energy transition concepts which can effectively reduce the CO2 emissions. For example, there are fossil-based energy plants already existing, as shown here in the figure, and we are trying to implement new renewable energy sources with conversion technologies and especially storages with the optimum system designed to reduce the CO2 emissions at minimum cost. And when we consider system operation in a coupling with the system design, then it leads to a coupled optimization problem, and which is computationally very expensive due to non-linearity in the physical modeling of system components, and the respective problem size increases and it becomes very computationally expensive. So far, we have, as Elias already explained, demo 4, we have our industrial partner in Germany, where we are trying to demonstrate our results, and we are trying to implement the new renewable energy sources in the energy transition concept. So here, our task is to cover the heat and electricity demand for this particular food and cosmetic industry with minimum CO2 emissions and the minimum cost. So what are the challenges here? On the right side, we can see the electricity and the heat demand of this particular industry, particular plant over the month, and also the daily heat demands. And here to provide this energy transition concept, there are 3 major challenges: that what should be the optimal choice of the components which are available among a large pool of components. For example, we have different renewable energy sources available, different conversion components available, different storages. So what should be the optimal choice, and how big, or what should be the optimal capacity of this chosen components, because which determines the investment cost at the end, and which is very crucial for any project. And how these components, the chosen components with optimal capacity, should operate in an optimal way that can be used to reduce the CO2 emissions. So there are 2 major objectives here, that we want to reduce the global warming impact, which is the CO2 emissions, and also to reduce the total annualized cost. And there, as explained, there are 2 optimization levels, the design and operation. We need to choose the component, we need to optimize the capacity, and also optimize the operating conditions. So it's a 2-level problem. It's also a multi-objective problem. So that's why it's the final type of this problem comes down to multi-objective coupled design and operation optimization, which is generally mixed integer nonlinear programming type of problem, which is computationally expensive. And explained, there are 2 major objectives: the total annualized cost, which needs to be reduced, or which needs to be minimized, which includes the system investment cost as well as the operation cost, and the global warming impact, which includes the CO2 emissions. And here, the design variables, or the capacity design variables, are the capacity of different components, what are the nominal capacities, and the operation variables are how much amount of electricity can be bought from the grid, or how much can be sent back to the grid, and what is the amount of the fossil fuel we need to buy from the grids. And there are particular constraints here, that we need to cover the heat and electricity demands, and the capacities of the components also has to be between some of the lower and the upper bounds. So this is basically the multi-objective problem that has to be solved during this optimization. And there are 2 ways of solving this coupled optimization that we have applied, a single stage optimization, which in a nutshell uses design and operation variables in a single stage. And these multi-objectives are solved with deterministic optimization methods with solvers like Kurobi or Baron. And in the 2-stage optimization, the optimization problem is divided in 2 parts, the design variables, design level and the operation level. And for each design level, the operation variables are optimized in a nested loop, and which is generally solved with different stochastic optimization methods. And at the end of the optimization, we get this Pareto optimal solution, because we have 2 objectives, as explained, that we have global warming impact as well as the total annualized cost. But as said earlier, like this is computationally very expensive to solve again and again. So how can we reduce this computational effort? So like first approach to reduce this computational effort is to somehow combine like a physics and the data-driven modeling or a surrogate modeling. And we have already published these results in the conference paper, which you can find later. So what is basically the physics? So everyone uses for a high accuracy like non-linear physics-based modeling, which are like which follows the physical laws and which are highly accurate. But the number of variables and constraints are like very high in this kind of modeling, because as the model fidelity increases in the physics-based modeling, the computational effort also increases, and which creates a higher computational effort. For example, in this pool of components, like when we integrated these components in the optimization problems, the variables per time step for these components are quite high, like for each time step. And the highest number of variables to be optimized for these components belong to the solar thermal collector and the heat pump. And the size of optimization problem becomes so large, like the number of variables and constraint goes into thousands, and which is computationally very expensive to solve. So we decided to somehow take these two components and try to model these components using the data-driven techniques. And so with the data-driven techniques, we trained these models, and we could reduce the variable per time steps for these two components from 5 to 6 to 2 to 3. And when we integrated these components in the whole optimization problem, the number of variables and constraint reduced up to 20 to 30%, which is quite huge when we have large amount of variables and constraint involved. And to so far, to create the data-driven models, we have used different regression techniques as well as the different artificial neural networks to find the best fit for the data-driven model to the physical model. And we have incorporated this different data-driven models into the optimization problem, which was shown earlier. And here we have compared the results with different kinds of modeling in the optimization problem with the reference physics-based model. For example, here, like the black dots, which you can see in both the figures in the single stage and two stage, are the Pareto front of the reference physics-based models of the components. And the other Pareto fronts with different colors are different combinations of combined physics and data-driven based models in the coupled optimization problem. And we have tried to find the best trade-off between the accuracy and time reduction for this combined modeling. And with this combined modeling, we were able to achieve the accuracy up to 91%, and the time was reduced. The computational time was reduced up to 37%, which is quite a lot when the problem becomes very complex. And we also compared the design capacity results with the reference physics-based and combined physics data-driven modeling. And the difference between both the designs for extreme points of the Pareto fronts were like 2% and 6%, which was quite acceptable. And we, as mentioned, SINNOGENES is all about integrating the new novel energy storage technology. So we have also included the thermal energy storage in our concept, and we try to simulate the results, the same kind of techniques with the thermal energy storage as well. And the accuracy for this concept was also achieved up to 90 to 91%, and the time was reduced by 30%. And these new results have been already published in one of the journals, which you can find in the later stage in the video. So far what we have shown is like we have tried to reduce the computational time. So far, like we for the whole year, like we used some of the reference days to represent the whole year. And here, like on the black dots, you can see the Pareto front with the reference days consideration. But in reality, we wanted to simulate the whole year optimization, which is again very time consuming and computationally very expensive. So we tried to compare the results of the reference days and the whole year, and we could find out that like when we use the time horizon for particular reference days, we lose so much potential for the CO2 reduction. So that's why like the optimal time aggregation method or the time compression methods are also very crucial when we try to provide the optimized capacity solution with the optimal operation. So the next steps or the ongoing steps is to develop a tool which is being developed right now, which considers all the different effects which we have shown so far, like different fidelity levels of modeling components, which includes the physics-based, data-based, low fidelity, high fidelity modeling, different input parameter interfaces with the SINNOGENES middleware, like the weather data, parameter data, constraint data, and different parallelization and the relaxation techniques like the time compression, time aggregation, linearization, and different solver implementation for linear problems, for non-linear problems as solved. And with this tool, we want to give the industries opportunity to take accurate and quick decisions for their energy concepts, for the novel energy concepts to include in the Energy Green Deal for the Europe 2050. So yeah, these are the conclusions and the next steps, which I've already explained about the high fidelity modeling, new relaxation strategies, different scenario generation using this optimization tool, and to validate this optimization tool with benchmark problems and the new experimental results, which we will get from our demo site. Okay, so that was all from my side. And
my name is Ricardo. Let me share my screen, please. So I'm from ISGAN, which is a research center in Portugal. And I'm going to talk about our work that's mainly focused on work package 4 for the project SINNOGENES. And it will be implemented in demo site 1 in Portugal. So our work started from a tool that we developed that was the outcome of several projects that we had in recent years. That tool aims to provide day-ahead schedule for specifically lithium-ion batteries, and it also included some types of curtailable loads and conventional generation. And we wanted to build on top of that to have a tool that was able to embark more battery technologies, more services. So for now, it was only focused on arbitrage, but we also wanted to provide system operating services, and also other types of loads like thermal loads and thermal storage also. So some of the main outtakes that we had from recent projects were that, for example, self-consumption optimization and operation cost reduction are correlated. This, I think, it's fairly obvious. So the more you use your renewable energy, the less you have to import from the grid, and your costs are reduced. So that is good on two ways. And the increased flexibility of a system earns greater savings. So the more flexible assets you have, not only batteries, but also other types of shiftable loads, you have the potential to have more savings and more self-consumption. And also we found that our tool is based on a mixed integral linear problem. And we found that, as Rushit explained, there are physical models that are very specific and very precise, but we can get good results if we manage to capture some fundamental dynamics of the assets from electrochemical models. I will talk about them in a second. And also the potential to provide flexibility services come from a multiple technologies and the aggregated management of those technologies. So our starting point, as I said, was a simple arbitrage tool that provided set points for the next day. And what we're showing here was the calendar for a day ahead of a battery. Sorry, I'm not showing my pointer. And what we managed to do here also was to provide a tool that could also provide curtailment set points that had minimum downtime and maximum downtime and minimum downtime for curtailable loads, and also could provide a simple schedule for conventional generation. Then in another project, what we thought was, okay, most industrial batteries are inside the container. That container has an air conditioning system, which can also be viewed as a load. So if the battery reaches a certain temperature, that AC is turned on, and that is a load that we could also try to incorporate in our problem. So we developed a simple model, thermal model for the lithium-ion battery that could take into account the temperature that was being generated by the charge and discharge of the battery, and to say, okay, let's try to not reach that temperature so that the air conditioning could not be activated. And another important starting point was a recent project that we had with the demo pilot leaders, that is CapWatt. And we are currently providing some set points for the day ahead for their lithium battery. It's an 800 kilowatt hour battery that they have now that they will also use in this project. And it is now being used mainly for arbitrage. So what type of models are we using? As I said, we use electrochemical models, which try to capture those fundamental dynamics of the battery. So for the lithium-ion technologies, what are those fundamental dynamics? First, maximum and minimum states of charge achievable depend on the magnitude of the charging and discharging power. So if we try to charge the battery at the maximum power available, it will not charge as much energy as if we use the less current, less power. And the same for discharging. And another important characteristic is that for smaller charging and discharging power set points, a constant efficiency model can be a huge overestimation. So usually you can find in the literature the so-called bucket model, which considers a constant value for efficiency, charge or discharge. And that is a good approach if you consider that you are using currents and powers that are close to the maximum. But if you try to use the battery with smaller power set points, and that is something that can happen if you provide other types of services besides arbitrage or peak shaving, you will enter a huge overestimation, as you can see here. This is the typical curves for the inverter of batteries that relate to efficiency with output rated power. And so another important thing from our models is that the parameters to feed those models and to build those models can be easily obtained either from the manufacturer's sheets or by a small set of easily done tests with the batteries in question. So you can perform some charge and discharge tests where you capture the voltage, the energy remaining after a full charge or discharge cycle, and the overall efficiency over the cycles that you perform in those tests, and you have all the parameters that you need to feed those models. So building on top of that, we try to increase the technologies that we had in our tool with, for example, vanadium redox flow batteries. And for that, we try the same approach. Let's try to find an electrochemical model that is based on the fundamental dynamics of those type of batteries. And which are those? We found that the energy efficiency is a nonlinear function of the SOC, the discharging power, and the electrolyte temperature. So we found a model that could be parameterized based on some tests, as we done for the lithium-ion battery, and we are now trying to fine-tune those parameters based on some data that we have. And the other important fundamental dynamic is that the maximum power that the battery can provide, while the output voltage is kept constant, is limited by the SOC. Now, this is an important assumption that we make because we are providing set points for 15 minutes. It's the minimum time step, the minimum granularity that we consider. We can say that the output voltage is relatively constant in that period. So if we are trying to come up with a model that was for transitory states, we could not have this type of assumptions. But we are considering a large enough time step to consider that, for example, the voltage is kept constant. And so maximum power is limited by the SOC, and we also have a model for that can be parameterized with tests performed over the batteries. Another thing that we wanted to add was a degradation, to consider the impact of degradation in the utilization of the lithium-ion battery. So for now, we are using a fixed cost that is applied to a discharge set point. So we try to condense all the degradation to the discharge cycle, because we assume that for every energy discharge, it had to be charged previously. So we condense all the degradation to the discharge set points, but we try to come up with a better model. We want to better that estimation of what is the cost of degradation to the battery. And we can see here in this GIF that by increasing the cost that is attributed to the degradation, the charge and discharge set points that are provided to a battery are more and more reduced, because it's less and less beneficial for the cost function to have those type of small charging and discharging cycles. And so we found also another algorithm that managed to to introduce the rainfall counting algorithm. This is the state-of-the-art degradation estimation model for batteries. And this algorithm counts the number of cycles that the battery has performed. And usually what you have from the manufacturer is how many cycles can you perform until the end of life. And so based on that, we wanted to estimate how much cycles we were performing on our daily schedule. And that is highly nonlinear. So we found a way to introduce the rainfall counting algorithm on our MILP problem. And we are now testing what is the difference between calculating the cycles post-delivery and within our model. We also want to increase the amount of services provided. So, as I said, for now, the objective functioning of the tool is based on arbitrage, but we also wanted to provide flexibility services. The main focus here is to provide automatic frequency restoration reserve and manual frequency restoration reserve with both batteries. So we are applying the lithium-ion battery and the vanadium redox flow battery to this service. And one of the main concerns when doing this within the optimization problem is to guarantee that if that band is activated, it will have the minimum impact in the rest of the schedule that was computed for the rest of the day. Finally, we also have recently one of our colleagues finished his PhD thesis, where he developed a mixed integer quadratic problem. It's not a linear problem, where he included several assets. He included the electric grid and also the thermal grid. He included thermal energy storage systems, cogeneration plants, and what he is trying to do now is to come up with a linear model, with a linearized version of his model, so that we can include all these other types of assets in our main tool. Just a quick overview of the demonstration site, which is in Maia, Portugal. So all these assets are owned by CapWatt. They have a decent amount of PV generation, a cogeneration plant, as I said, a lithium-ion battery, 800 kilowatt hour, 320 kilowatt peak. They are currently procuring the vanadium redox flow battery. FEOP, the Faculty of Engineering, which is also working with us, is developing a prototype of a thermal energy storage that will also be included in the site, along with other assets. And the final look at our tool and how it will integrate with the demo site and also with the SINNOGENES middleware is we will deploy it in a server as a Docker container. It will work as a REST API. It will make requests for load and generation forecasts from the middleware, and leveraging on our current connection with CapWatt, we use an SFTP server where we provide them with the set points for the next day for their current battery. and the system operator there, the SCADA operator, will decide if it can and if it will provide those set points for the lithium-ion battery and also for the vanadium redox flow battery for the next day. So with this, I conclude my presentation. Thank you for your attention.
Okay, thank you, Ricardo, for your presentation. I'm Ángel Hernández. Let me share my screen. Okay. Yes, I'm going to talk about. Sorry, I'm going to talk about some other activities to be developed here in SINNOGENES project. But first, I want to introduce you the two Spanish demos that we have here in the project. The first of them is the demo site 2, is located in Soria. Here we have a very huge microgrid, more than 4 kilometers length. We can operate it in radial and rig modes. We have connected to the general supply grid through the main transformer that converts the 5 kilovolts into 15 kilovolts to 15 kilovolts, and after that through our 8 transformer station we convert into 400 low voltage. We have several distribution systems. We have along over the area. We have a nominal power of PV plant around 360 kilowatts. We have also some wind turbine system distributed also along all the area. And we have a total power of 160 kilowatts also. We have another storage system like lead-acid batteries, lithium batteries, and hydraulic storage. The consumption, we have industrial and domestic patterns, and we have our own energy management system that we can monitor all the elements in real time. We have a remote control, and we also store the data in our system. This is a general scheme of the communication protocols. We communicate through another software, and we can manage all the alerts through emails and through mobiles apps. And with the human machine interface, we use home assistant software. It's free also. We monitor all the data by second, and we store it in MariaDB database by 15 seconds. By 15 minutes, sorry. We have encrypted access to all of these programs. Moving to the demo site 3, is located in Huesca. Here is the plot plan of the 14 buildings that are connected to the microgrid. They have also around 700 kilowatts of photovoltaic systems and more than 600 kilowatts of distributed in 3 wind turbines. This demo site is focused on hydrogen. Here in the upper part we can see the hydrogen refueling station, and here in the bottom part of the slide we can see the electrolyzers. This is a general scheme of the SCADA system, of the energy management system. They are connected to the grid as well as we do. They transform their 45 kilovolts into 15 kilovolts, and they distribute their grid into several substations, and they have connect here all the buildings, all the meteorological registers, and also the INICOM office that they are the responsible of this demo site. Here we focus on the hydrogen installations. They have some charger for their vehicles and the hydrogen refueling station that is stored the hydrogen here in their deposits. Moving to the activities, we have focused on 3 different activities. First of all, it's related with demo 2 in Soria. Is the optimal operation of district heating and cooling system using geothermal storage. The objectives of this task are combine the electrical microgrid and the thermal network to enhance renewable energy management. And we are also testing seasonal thermal storage versus a conventional model. We are going to build or to drill 4 new boreholes with 180 meters depth here, located between our existing borehole of 85 meters depth to create an operational geothermal field here in the north part. And we have another extra for boreholes that we will be used to use as the comparative test area. We are also going to install a new prototype of a geothermal heat pump, and we pretend to use the subsoil as energy stationary storage. We pretend to extract heat from the building in the summer period to introduce in the underground, and in winter period we pretend to extract this heat and use to heat the building. This is an scheme of the system. We pretend to provide renewable energy, electrical renewable energy to the heat pump. Moving to the other use case, to the other activity, will be the provision of fast flexibility services from the distributed energy storage technologies. The objectives are the suppression of power spikes with a period less than 10 seconds. And we also pretend to manage the energy in short time frames with a period less than 15 minutes and increase the voltage stability and provide the frequency regulation. Regarding the step, first of all, we will install this prototype of fast response energy systems. After that, we make an individual testing. We will integrate in the grid, and finally we provide these fast flexibility services. These are some figures of the 2 prototypes that we will install here in our demo 2. One is the neutral capacitor bank with a maximum power of 120 kilowatts, but not so much energy stored. And the other prototype will be a flywheel with a nominal power of 25 kilowatts. This is a general view of the container. Here in the left part, we will have the supercapacitor bank, and here in the right part, we will locate the flywheel. We have just finished the installation of the coupling of this decoupling converter that is connected to the 15 kilowatts microgrid, and this equipment is capable to modify the frequency of the voltage of the microgrid. We pretend to use this equipment to make these modifications of the frequency and the voltage of the grid, and we are going to try to make it stable with the supercapacitor bank and the flywheel. The other activity, the high-level use case 5, is related with demo 3, sorry, power to gas for local community energies. This is focused on the power to gas potential within the local communities by utilizing electrolyzer and electrical vehicle chargers balance renewable power production. The objective is to optimize the matching of renewable energy generation with hydrogen production for the supplying hydrogen refueling station, where it also consider the full stack market price. The objectives shall be optimally match the renewable energy sources generation with the hydrogen production, operating couple gas and electricity networks in local energy communities. We pretend also to trade with the energy prices, and the final objective is decarbonization of the technological park. The business cases are focused on local energy markets, the sale of cheaper electricity for nearby buildings, plus the minimization of the system losses. Consider the possible simulation with the blockchains for buy and sell for trade this energy. It is planning to optimize the use of the refueling station, considering the need of hydrogen in the vehicles and other consumption things. and they pretend also to use the recharging points in combination with photovoltaics to minimize the cost of electric recharging of electrical vehicles. In all of these activities, we have proposed some scenarios that are similar in the three activities. First of all, is a pre-qualification scenario. After that, we propose an efficiency scenario with a standard operation, and the last one will be the pro-efficiency with an optimal operation of the full microgrid. Moving to the conclusion and remark of all this webinar. Renewable energy and storage should go together because both support decarbonization in a complementary way in all sectors. Once you favor or support the one, you do the same for the other in order to support the decarbonization target. The digitalization and business model are two important pillars that we can foster storage with integration into the grid. Development and integration for an optimization tool for the definition of an optimal energy supply system based on renewable sources, as well as its operation for the decarbonization of industrial process. Data-driven modeling combined with physics-based modeling and parallelization techniques to reduce computational efforts. Development of an optimal scheduling tool for multi-technology storage system, including lithium-ion batteries and vanadium redox flux batteries based on mixed integrated linear problem. Development of linear model for the redox flux batteries that capture the fundamental dynamics of its operation using in a linear problem. Integration of the rain flow counting algorithms in a mixed integral linear problem to estimate the degradation of storage system based and consider its inherent cost in the objective function. Inclusion the possibility of participating in day-ahead flexibility market in basic linear problem through the definition of operation band shapes by storage activity. We also pretend to integrate electrical grids and gas with gas and heat networks that will provide greater flexibility in resource management and enable synergistic opportunity for combined storage solutions. Incorporating a cutting-edge monitor and control technologies into the current grid is essential for achieving optimal energy management and accomplishing the decarbonization target. And finally, the implementation of fast response energy storage prototypes is crucial to ensure the resilience and stabilization of the current grid infrastructure. That's all from my mind.
For the question and answer session, so I kindly invite the audience to pose their question using the question answer tool, if any, so that well, the speakers can like clarify any doubt or like answer to any curiosity that you may have. And okay, and starting with this, at the end, SINNOGENES project are European Union funded projects, and it goes in the way of achieving the European Green Deal targets. Maybe you can like describe how the SINNOGENES energy storage solution can contribute to this, and which role the project has on achieving the Green Deal targets.
I can provide some feedback on this question. Matteo, practically the intention of the SINNOGENES technologies are to facilitate the penetration of renewables into the energy mix. Storage technologies is of vital importance for this in order to alleviate, let's say, the volatility of renewable energy sources. And also on the other side, the SINNOGENES projects is providing a lot of innovative technologies to valorize different sectors and different, let's say, elements of storage technologies. Thermal storage, hydro pump storage, and hydrogen presentations in order to have the maximum result for renewable penetration, and of course achieving also the reliability and resilience of the grid. I don't know if any other would like to add something or.
And well, you maybe can complement in the line with this achievement of the European Green Deal targets, which is the strongest element of the innovations that the project is proposing and developing.
In my opinion, there are several issues that somebody can find in this wide developments. The strongest issue from my side is that leveraging very many different technologies and many different sectors, and showing how this can be integrated into the electricity grid, because practically all the sectors that can provide storage potential, as well as the demand sectors that are, let's say, served by the energy, all of them are going through the electricity grid. And also it supports very much the targets for electrification of the different sectors. So I believe the great variety and the demonstration in different areas is a strong point of SINNOGENES.
Okay, thank you very much. There is a question from the audience that asks for clarification about the scalability of the solution. So the question is, when will these demos have mass application, for example, at the TSO level?
I can provide some answer, and maybe also Angel and Ricardo and Rushit can also complement. We are working now at pilot sites, specific pilot sites, and we are testing specific high-level use cases to deliver some flexibility services. We will have a dedicated tasks for evaluating the replicability and scalability of the solutions, as well as their overall impact in the energy mix. However, the microgrids that they are tested are real electricity grids that are connected. I think also maybe Angel can also complement me on this about the microgrid of CMAT. They are also connected to medium voltage and also to electricity markets that they can, let's say, deliver their services once the technologies, of course, go into higher readiness level.
Yes, from our sides, we are going to provide flexibility service on medium voltage microgrid. Right now, we have, as I mentioned before, installed an equipment that can vary the frequency and the voltage of the 15 kilovolts grid. So I think it's very important to test these prototypes to make stable this parameter of the grid.
Okay, thank you very much. And maybe related to flexibility provision, since you're testing solutions that can support power system operation, what do you see as a key enabler for increasing the business opportunities of storage as a flexibility provider?
I can try to answer that one. I believe that an aggregated management of all assets within the microgrid are essential for the provision of those services, because only bulk provision can concerted action of all the flexible assets within a microgrid, especially the storage systems, can meet what DSOs and TSOs may require, because for example, from our experience, we found that the amount of flexibility that can be provided from a single asset may not even if the asset is very big, may not achieve the minimum requires that a system operator may need at a certain time. So we are also not in this context, but also, for example, in the context of renewable energy communities, where we have more and more assets available to provide those type of flexibility services. Aggregation and consultation of their management is I believe is the key here, and different types of assets. So ones that are more, as Elias explained in this presentation, more for bulk energy provision and others for more dynamic transitory energy provision.
Okay, thank you very much. And so we are, well, there are no questions for the audience, but we are like achieving the end of the webinar. So maybe we can close the session with one last question, and also please feel free also to like conclude with your final remarks that you want to give to the audience. So, for example, if you can please comment on the key expected outcome of the SINNOGENES project, so which is the legacy that the project will leave to the community, and how it can contribute to improving the decarbonization of our society.
Yeah, I can start. So according to my point of view, like all over the world, the green energy transition is happening now, and it's like the most needed solution so far. So everyone is going towards the new renewable energy sources, and day by day we are having the abundance. Like maybe in the future we'll have the abundance of the green energy available, and to utilize this green energy in a more flexible way, we need the storages. We need the optimal storages which can be used in different kind of processes. And these demos, the 6 demos, will be able to showcase not just EU but even in the research field all over the world that this can be done with optimal amount of effort. Thank you.
Thank you, Rashid. Well, so please, Elias, Ricardo, and Angel, so feel free to, to share with us your final remarks. And
thank you very much. It is a great opportunity to, let's say, to dedicate this time to talk about storage. Storage is, let's say, getting more and more important for the energy system. We can see it everywhere. We can see it in the efforts of regulation regarding the latest demand response network code that talks very much about storages. We can see it in the sector coupling approaches. We can see it, let's say, in all the efforts of research and innovation. So I think it's a very good timing for this project.
Yes, and I'd like to add that from our side, it's good to see that faculties, research centers, companies are all focused on how important storage is, how much it can give in terms of the introduction of renewable energy sources and cost reduction also. So everyone is very keen to experiment and to engage in new storage technology and to tap on its potential. Yes.
Just to complement some comments, I think it's very important to manage all other problems that we can arise regarding the integration of all this renewable energy into the grid system. And from SINNOGENES, we are trying to have some solutions to, for example, the stabilization of the grid, the integration of different heat, gas, geothermal into the electrical grid, and we are working on that, and we hope we find very good solutions with this investment.